Lab 1 by Madeline Gaffney. Lab 1 required me to observe the motion of an object from my surroundings that moved with a constant velocity. After recording the object, I needed to use the computer software Tracker to analyze the motion and extract its position. I then used the software VPython to predict the motion and position of the object. The objective of the lab was to find the relationship between the object's observed and predicted motion by creating a position versus time graph using the results obtained from the analysis in Tracker and VPython. I discovered that the slopes for the predicted and observed motion on the position versus time graph were very similar, except that the velocity of the experimental position was not as constant and moved with greater velocity toward the end of the time interval. The object whose motion I chose to record was a cylindrical stool that I found in the Kolk. My friend recorded me as I pushed the object, causing it to move at a nearly constant velocity after some initial acceleration. Here is the original video of the object's motion. I imported the video into Tracker so that I could analyze the object's motion using this software. First, I adjusted the time frame of the video in order to eliminate the initial acceleration and analyze the object only at its constant velocity. I set up a coordinate axis using the center of the object and its initial position as the origin and used the calibration stick with the width of the object. Then, tracked the object's position in the negative x direction as shown by the line of red diamond shapes. As a result, a table of position time coordinates can be seen in the bottom right corner, and the position versus time graph of the object that these points produced can be seen in the top right corner. I used Tracker in order to determine the object's initial start time, which was 0.033 seconds, and determine that its initial position was at 0.002 meters by looking at the position versus time coordinate table. I calculated the initial velocity by using two position time coordinates from the table on Tracker and dividing the change in position by the change in time of the 2 points. The last observed time of motion was 1.002 seconds, and the object's mass was 4.08 kilograms. I used the initial conditions of the experimental model as the initial conditions for the computational model. I modified the Python code using these conditions as the input for the object's mass, initial position, initial velocity, and start time. I updated the while statement of the Python code by inserting the last observed time of the object's motion. Since the velocity is constant, fnet is equal to 0, so I updated the vector for fnet to reflect that. Lastly, I modified the equations determining the object's final velocity and final position in order to accurately reflect Newton's second law. I ran the modified Python code with the initial conditions from the experimental model, and this is what my code produced for the predicted motion of the object. The green line shows the object's path of motion in the negative x direction, and at this point, the blue ball shows the object's final position. The position versus time graph of the computational model can also be observed. As I said earlier, I had to set up a coordinate axis for the object's motion. When I recorded the object's motion, I rolled the cylinder from the right side of the frame to the left side, resulting in the object moving in the negative x direction. If I had flipped the coordinate axis and rolled the cylinder from left to right, the object would have moved in the positive x direction, which would result in a position versus time graph with a positive slope rather than a negative slope, because the position values would have been positive instead of negative. In the computational model, I set the net force equal to 0 in order to predict the motion of the object, but it is not entirely possible to determine every force pushing and pulling on the object. In order to relate the computational model and the experimental model, I have displayed both the Tracker and VPython analyses of the object. The visual model of the predicted object's motion produced by VPython is comparable to the Tracker model of the observed object's motion since both move in the negative x direction. This similarity is reinforced by the two position versus time graphs, which also appear to be very similar to one another. The experimental and computational models do not completely match. This could be due to the fact that the computational model does not account for friction, the experimental object's velocity might not have been completely constant, or the object might not have rolled in a straight line. Although the observed and predicted positions do not match perfectly, the computational model predicts the observed object's motion pretty accurately. The discrepancies between the two models can be taken into account in order to better future experiments.